to lesson 2 of Unit 9. And today's lesson is called Limiting and Excess Reactant. And so what we're going to do today is take some of the basic stoichiometry principles that we learned from lesson 1 and kind of apply them to more of a real-life lab scenario where instead of just being given one reactant, you're given all of the reactants, and we're trying to figure out how much product will we actually get out as a result of combining kind of all the reactants together. And so today we're going to cover the first 3 learning targets. So one is differentiate between, or tell the difference between the terms limiting reactant and excess reactant. Then be able to identify the limiting and excess reactant, and be able to make a particle drawing that kind of represents the effect that the limiting reactant has on the reaction. So let's start off with kind of our first learning target and just get a good idea of what is the difference between a limiting and excess reactant. And say probably, just by the words limiting and excess, you already have a good idea of what they do. So the limiting reactant is whichever reactant is completely used up first, all right? And so therefore, it determines or limits how much of each product can be made, and it also limits the amount of the other reactants that are used. And so the idea is that when the limiting reactant runs out, the reaction stops. And so that means no more reactants are used, and also no more product is made. Then on the flip side, you have the excess reactant. And that's the reactant that's left over or in excess once the reaction is complete. And sometimes, kind of just to save time, you'll see those abbreviated ER for excess reactant and LR for limiting reactant. And so what let's do first is let's kind of take a look at the particle drawing side of things and see if that gives us some insight into how this limiting excess reactant stuff works. So we'll zoom in on our first example here, and it just says identify the limiting and the excess reactant. And there are a couple ways to kind of go about this problem, but the easiest one is if they happen to tell you what the product looks like, you can easily figure out the limiting and excess reactant from there. So here they have a reaction where we're combining hydrogen and oxygen to make water. This is a synthesis reaction. We've got 2 simple elements coming together to make a compound. Now, if we count kind of our products, we see that we have 1, 2, 3, 4, 5, 6 water molecules. And if we kind of put these little hydrogen atoms together, we have left over 1 hydrogen molecule. Now, if you'll notice, we don't have any of the oxygens left over because they've all been used in making the products, okay? So if we had to assign limiting and excess reactant, we would say that the oxygen was used up first. It was the limiting reactant. On the other hand, the hydrogen was left over at the end, and so it is the excess reactant. There was more than enough hydrogen. All right, so now let's see if we can figure out the same thing when they don't give us the product to start with. So let's go to example 2. So example 2 says identify the limiting and excess reactant, then draw the product. All right, so now what we need to do is we need to pair up the hydrogen molecules with the oxygen molecules to start making some water. And our chemical equation is going to be handy here, because what it does is it tells us that for every 2 hydrogen molecules, you should need 1 oxygen molecule, all right? And as a result, that should get you out kind of 2 molecules of water. So if we kind of start crossing this off here, so we need to use 2 hydrogens per every 1 oxygen. So 2 hydrogens per 1 oxygen. Uh-oh. Now it looks like we only have 1 hydrogen, but we have 2 kind of extra oxygens, all right? So we would be only able to use kind of a part of this extra hydrogen to only generate 1 more molecule. So for example, these could kind of combine, but that would leave us with kind of an extra oxygen atom all by itself, and then kind of a complete oxygen molecule. So let's kind of go ahead and draw that product in right quick. So we know that we're going to make 4 water molecules because we were able to complete this 2-to-1 ratio 2 times. So that gives us 4 waters. So we'll kind of draw that in there. Okay, there are 4 complete waters. Then we know we're going to have 1 oxygen molecule left, 1 spare oxygen atom, and then finally we had one more water molecule from this combination right here. All right. So now let's kind of label again our limiting and excess reactant. So we had some oxygen left over. It was more than enough. So it's going to be our excess reactant. The hydrogen we ran out of. It limited how many waters we could make. So it is our limiting reactant. Okay. And so that's the idea, is you can only make as much product as the limiting reactant will allow. But here's kind of the catch. Oftentimes when we're working in the lab, we don't have a tool that lets us get down on the molecular level and actually count these little molecules like we did in the particle drawing. We can't pair them up. We can't see with our eyes, exactly how much of the product that we'll make. Instead, what we often have in the lab are a balance which reads in grams, all right? And so the only way we can kind of decide what's going to limit us is by doing some calculations. Okay. Now, right quick, before we go to the calculation part, I want to ask you kind of a key question that students often have sometimes. And so it says to us to look at both examples above. Is the limiting reactant always the reactant with the fewest starting molecules? Okay, so let's go ahead and count and just see what we find. So in our first example, there were 3 oxygen molecules and 7 hydrogen molecules. So far, on that example at least, it looks like the limiting reactant had fewer molecules than the excess. Now let's go to our second example. Here for hydrogen, we had 1, 2, 3, 4, 5 molecules. And for oxygen, we had 1, 2, 3, 4 molecules. Now, this case kind of goes against the question in that the limiting reactant was not always the reactant with the fewest starting molecules. Okay? So in that case, hydrogen was limiting even though it started out with more molecules. So kind of the answer is no. The limiting reactant is not always the reactant with just the fewest number, all right? So we can't just look and say, oh, there's less hydrogen. It must be limiting. Because in this case, there was more hydrogen and it was limiting, all right? So no, and let's see if we can think about why or why not. So if you look at the chemical reaction, this is kind of the key here. The reason that the numbers of starting molecules themselves don't determine limiting reactant alone is because the molecules react in different ratios based on the chemical reaction. It took twice as much hydrogen as it did oxygen. So for example, if we started with 4 oxygens, we would have needed 8 hydrogens to react with it completely. So the idea is no, we have to account for the ratio, and I'll specify here, we have to account for the mole ratio between reactants. So not everything is a 1-to-1 ratio. Sometimes you may need double or triple the amount, and that kind of affects which reactant comes out as limiting. All right, so now let's talk about how to determine what the limiting and excess reactant are when we don't have those pictures of our particles. So what it's going to center around is this key fact that the limiting reactant is the reactant that produces the least amount of product. It limits how much is made. So what we're going to do is we're going to pick a product and then check both reactants to see which one gives us the fewest moles of the product you chose. All right. So here's what we're going to do is they give us information about each of our reactants. So in this first problem, we have 0.30 moles of zinc, and we're reacting it with 0.52 moles of hydrochloric acid. And so we're going to set up kind of a workspace for both of our reactants. So here's zinc, and then here is hydrochloric acid. Now, what we need to do is we need to pick a product. Now, it does not matter which product you pick. So we can either pick zinc chloride or hydrogen. Let's just pick zinc chloride. He's our first product. So now what our goal is we want to convert both reactants to moles of zinc chloride. If we're both converting them to the same ending point, then we can compare and see which one gives us less product. The reactant giving us less product will be limiting. All right, so let's start out here. If you notice, they give us our reactants in moles, which means we are immediately ready to use the mole ratio. So there's no need to go into molar mass on this problem. So what we're going to do is we're going to copy down our units to the bottom. So moles of zinc goes on the bottom. And then for moles of HCl, that gets copied to the bottom as well. And the idea is the moles of our product, zinc chloride, goes on top. So now we go back to our reaction and we look for our mole ratio. We have like no coefficient shown in front of zinc, which means that it has a coefficient understood to be 1. Hydrochloric acid has a coefficient of 2. And then finally, I'm going to change my color for zinc chloride here. Zinc chloride also has a coefficient of 1 as well. There we go. So it's a 1-to-1 ratio for zinc, and then a 2-to-1 ratio when we're using hydrochloric acid. Then we'll be able to solve. So for the first part, it's just 0.30 times 1 divided by 1, which is still the same amount, 0.30 moles of zinc chloride. Then on the bottom problem, it would be 0.52 times 1 divided by 2, which gives us 0.26 moles of zinc chloride. All right. So now we ask our question, which reactant gave us less product? So here, the hydrochloric acid gave us less product, so it is the limiting reactant. The zinc gave us more product, so it would be the excess reactant. And so even though we started with more hydrochloric acid, because of that 2-to-1 ratio, it ended up being the limiting reactant. And so again, each of these problems, just like lesson 1, will use the mole ratio because every reactant kind of reacts in a different amount. All right, let's try one more problem and then we'll let you practice. Thanks for hanging in there. All right, so same setup, they give us 2 different reactants based on the same equation. All right, so here we have 0.45 grams of zinc, and it's reacting with 0.67 grams of hydrochloric acid. Okay, and it says identify the limiting and excess reactant. So again, what we have to do is pick a product and decide which reactant gives us less product. So just for fun, let's try the product hydrogen this time, just to show you that it works no matter which product you pick. All right, so now we want to convert both of our reactants into moles of hydrogen. But if we notice, they're not quite ready to do that yet because they're in grams. So before we can use the mole ratio to get the hydrogen, we need to take each of our reactants to moles first. And that's your common step. If you start in grams, you need to go to moles before using the mole ratio. So what we'll do is we'll go to the periodic table, we'll look up zinc, which has a molar mass of 65.39 grams. Molar masses are always per 1 mole. Then we'll do the same for hydrochloric acid. We'll take hydrogen's mass, which is 1.01, and add it to chlorine's mass, which is 35.45, and that gets us 36.46 grams, again, per 1 mole. Now that we're in moles, we're ready to use the mole ratio to take each reactant and convert it into moles of products. That way we can compare. So we've chosen to use hydrogen as our product, so I'll put moles of hydrogen on the top. Again, anytime we're going from moles of reactant to moles of product, that requires the mole ratio. So for hydrogen, it has a coefficient of 1. Zinc also has a coefficient of 1. And, should say HCl at the bottom, sorry about that. And HCl has a coefficient of 2. We're now in the same unit, moles of hydrogen, so we're ready to compare. For our first problem, that would go into our calculator, 0.45 divided by 65.39 times 1 over 1, which is just the same thing. And so that gets us 0.0068 moles of hydrogen. Then for our last example, that would go into our calculator, 0.67 divided by 36.46 divided by 2, and that gets us 0.0092 moles of H2. All right. So now what we see is that the zinc gave us less product than the hydrochloric acid. And so if we write that in over here, so zinc is the limiting reactant, which means that hydrochloric acid is the excess reactant. And I'm realizing I forgot to point this out when I worked the first problem, but the reactants, when we say like this is the excess reactant, we're really referring to the reactant that we started the problem with. So technically I should add in zinc and say that zinc, is the excess reactant and that hydrochloric acid is the excess reactant. These values down here, these are for the product. So this would be our excess reactant and this would be our limiting reactant. So we just need to make sure we're labeling the correct part there. All right. And so again, definitely let me know if you have any questions. This just takes some practice to really get down pat, but I totally know that you can do it. All right. Good luck and thanks for watching.